developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
The work we do in my lab is to design computationally effective methods for 3D reconstruction from 2D bearing-only sensors, such as cameras. The reason why we focus on cameras is because they are low cost, compact, and easily deployable in different platforms from air to ground. The problem we're looking at this project is to develop a real-time 3D image technique, turning full motion videos into 3D navigatable dynamic environment using a technique called 3D Gaussian Splatting. Traditionally, this was done by using 3D polygon meshes, which are very difficult to optimize and easily polluted by noises and creates distortions that is geometrically inconsistent. The idea of 3D Gaussian Splatting is to present the 3D scene with optimizable Gaussian ellipsoid, with its properties such as locations, shape, color, and opacity, which helps to fill the voids and presents a much better visual quality. More importantly, these properties can be easily optimizable by using frame-to-frame differences from the full motion videos, which allows us to create 3D scenes with moving pedestrians and cars over the time.
You can create this real time as transparent sky is flying around. We can turn around, take these images and create RF pseudo models, you might say, or synthetic radar capability from these structures as we get sort of the 3D capability. So the interest for AFRL to collaborate with Ohio State and Transparent Sky is to incorporate the RF with the EO splatting capability, and I think this will be revolutionary.
Since the start of the project, we've made a great progress in validating the possibility of constructing and rendering dynamic Gaussian ellipsoid of the scene by using only video frames from the drone. Given an input full motion video, we have developed a process that combines 2D, 3D vehicle tracking and 3D reconstruction techniques to construct a 4D dynamic splatting, Gaussian splatting field. The reason why we call it 4D is because it allows the users to freely navigate the scene at the same time observing the moving objects. Here's one example. You can see this is a short video clip from a drone video footage in which the drone is flying and capturing videos of the scene. But at the same time, the vehicles are moving along the street. Using our method, we are able to convert this full motion video into a dynamic Gaussian splatting model, in which we can freely choose the viewpoint of the model and observe this dynamic scene at different angle, and even at the viewpoint of the surveillance camera. While the results are still preliminary and require further improvement, some of the components have already been sent to our industry partner, Transparent Sky, to be incorporated into potential products with a higher readiness level.
Over the past 6 months, we've been working on a pipeline for live 3D Gaussian splatting as a means of creating a much more realistic, accurate, and detailed representation of areas under military surveillance. We'd already worked out the remainder of the end-to-end pipeline through our prior work on live 3D imaging. This included capture and stitching imaging homographies, developing sparse and dense 3D models at unprecedented speed, and transmitting relevant pieces of imagery in real time. The process of registration and overlay had to be developed to a precision of approximately 2 meters from miles away. 3D Gaussian splatting builds on this progress, giving models that are free of most of the artifacts that are seen in traditional 3D models. Today, we're working out the details of the pipeline to create a highly compressed data stream of realistic, immersive reality that can potentially become a new means for representing the world, as well as storing histories and sharing imagery with wide audiences. The pipeline includes unique methods for detecting change in scenery, in which even slow and subtle changes are detected and modeled. Both Transparent Sky and Ohio State have made contributions to these techniques. Both organizations have also made substantial progress in developing representations of changing or moving objects quickly so they can be used in motion-oriented real-time models.
We are currently in the process of training a unit-based image-to-image generation deep learning network that can provide that additional knowledge. It does that because it is being trained on thousands of 3D objects that are representative of the 3D objects that we generally see in the scene. We are also exploring shadow removal techniques to improve our change detection. When lighting conditions change, due to sun angles, clouds, etc., change detection becomes a much harder task. We are exploring two main avenues to handle those discrepancies currently.
Over the last 6 months of research, we've had a tremendous progress. In this time, we have updated our algorithm and developed a more robust and accurate dynamic object detection approach to better support our 4D Gaussian splatting model. Here in this video, we show a side-by-side comparison between our previous and new results, respectively on the left and right side. If you focus on the marked vehicle in the red box, we can see that the new results, because of the finer detection of the moving objects, have significantly improved the quality of the rendering. More importantly, we are able to apply our approach to the Transparent Sky's WEMI data, which can be used to cover a much larger area for ISR. Because the algorithm is in its early development stage, it currently runs at a rate of 0.1 frame per second. Moving forward, we will focus on two aims. First, we will accelerate the detection to a factor of 20 and then integrate the 4D Gaussian splatting model to Transparent Sky's WEMI system to allow a full-scale and near real-time system for use.